So we're going to come to the concept of interference. Interference here is used slightly differently from how we use it in English. If I'm doing some work and you come and you keep talking to me, then you're interfering with my work, so it doesn't get done. That's not necessarily the way we use it in physics. Okay, the way you use it in physics is when two waves occupy the same space and time, okay, at the same time, then they interfere, so you have superposition of the waves to give a resultant wave. Then they may move in their own directions and move out without having any effect, permanent effect on them. So it's just in that space and time when they overlap that you have an interference phenomenon. Okay, so for example, if say this black dot here is the source and it's producing the same sound waves, one is traveling here to a speaker S1 and the other is a red one traveling here to a speaker S2, okay, then this one is occupying one wavelength, 2, 3, 4, 5, and 6 wavelengths, yeah? And this one, 1, 2, 3, 4, 5, 6, 7, and 8 wavelengths, yeah? So if the path difference is an integral multiple of lambda, which it is, it's 2 lambda is the difference, this one needs to travel 2 lambda more than this one, then we get constructive interference. Yeah? So if my path difference is an integer multiple of lambda, or if it's 0 multiple, so there is no difference at all, both travel exactly one wavelength, there is no path difference, then so any whole number, 0, 1, 2, 3, and so on, will produce constructive interference. So what's happening at the point where they overlap in space and time is that here's the first one and the second one, okay, they're exactly in phase with each other. What does that mean? That means that when this has a maximum, this also has a maximum. They go through 0 at the same time. They go through their minimum at the same time. Then we can get constructive interference by simply adding the two. Yeah? Completely constructive interference. What if their path difference was such that it was not an integer multiple of lambda, but say of lambda plus half a wavelength, okay? So if I had some integer plus half times the wavelength, and it doesn't matter whether n is 0, 1, 2. So here it shows the two waves shifted by half a wavelength, right? The zeros correspond over here, but this has a maximum, and this has a minimum. The zeros correspond again. This has a minimum, this has a maximum. So here we have two waves that are 180 degrees out of phase, yeah? And when they overlap, here's the first one, and here on speaker 1, here's the second one, and you can see that the resultant is a completely destructive wave. So this is destructive interference, yeah? Okay. So if we use this concept and we produce a wave on a string with two ends fixed, okay, then we know that if we produce the wave from one side, it's going to get reflected from the other side, yeah? And it may get reflected in phase or out of phase. If the end is fixed, it's going to be out of phase exactly, right? So the forward wave and the backward reflected wave are going to interfere because they're in the same space at the same time. And they will produce at certain frequencies a wave that appears to be standing still. It's called a standing wave, okay? Those frequencies depend on the length of the string, okay? So we're going to see that. So consider a string. This is my string here. It's not actually shown. It's shown when you are seeing the first standing wave. So when it appears to be a first standing wave, you're going to see something like a segment like this. It's oscillating so fast between these two positions that it appears to split and give you a segment n equals 1. This is half a wavelength, right? Just look at one side of it. This is a pretty long wavelength. That's 1/2. If it continued along the string, then that would be the second half. This would make one wavelength, yeah? However, we don't actually have string here on this right side of these two blue poles. where the string is tied. Yeah. So all we can generate is this part of the wave. So our length L for the string, let's say the string has some length L, that's equal to lambda 1 over 2, yeah? Half the wavelength. Or lambda 1 equals 2L. This is the longest wavelength we can get, or the shortest frequency, the first frequency. So this is the loop we said produces one loop. Now where it oscillates the most, it has most freedom, we call it the antinode. So we denote that by an uppercase A. And where the points are fixed, over here the string is fixed, those are nodes. Okay? So note that between two nodes, there's always an antinode, and between two antinodes, there's always a node. Okay? So you will also find that certain other frequencies are also possible in this. The first lowest frequency is called the fundamental, or the first harmonic, okay? And then you can get higher harmonics, second, third, and so on, which are integer multiples of this. And this can also be called overtone. The first overtone is the second harmonic. So fundamental, then first overtone, second overtone, and so on. Okay. Do not get confused in the way of counting. Follow one system or the other. Either you go fundamental, first overtone, second overtone, or you go first harmonic, second harmonic. So first harmonic and fundamental correspond to each other. You do need to know both terms, okay? So the length of the string selects which frequencies will produce the standing wave, okay? All others will get damped out. So now we look at it in a little more detail. Here's my original string. Okay, then we change the frequency, and at a certain frequency, you get the first harmonic or the fundamental, which is this one. Remember, we see just one segment, L equals lambda over 2. We did this on the previous slide. If you keep changing the frequency, then at the frequency F2, you are going to suddenly see two nodes, so you see the entire wavelength fitting in. Here's my node. Another node has come in between these two. Originally, we had just two nodes. Now we have another node and corresponding antinodes. So I now see two segments, one segment and second segment. And my length of the string, which is this length, now equals the wavelength here, which is lambda 2. Okay? And then I can introduce another node by changing my frequency further. You see more and more frequencies are fitting in here, more nodes. So L equals 3 lambda over 2. And we get a general formula where for any number of nodes n equals n times F1, where F1 is the frequency of the fundamental. And we know that on a string, the fundamental frequency, we know the velocity formula, so let's get it from there. Okay, we know on a string, we saw this before, that if F is the tension in the string, and mu is its linear density, yeah, this is mu, then this is the wave velocity, but v is also equal to f lambda. We saw all of this in the previous chapter. So if f is my fundamental, then it's f1, lambda 1, yeah? So f1 equals velocity, which is this part, divided by lambda, and lambda is 2L divided by n, yeah? So this part comes from the lambda, this part comes from v. Okay, you need to know this formula.